Continuing our discussion on simplifying and operations on radical expressions, let's take a look at this first problem, square root 8 plus square root 2. At first glance, it seems that they are not like radicals, but if we work to simplify the square root 8, because it has a perfect square factor of 4, we may be able to obtain like radicals. That is the idea for this entire section. 8 is equal to 4 times 2. I'm going to keep this plus root 2 here at the end so I don't forget to add it. And then using the product rule for radicals, I can split that square root across that multiplication of 4 and 2. We know from past experience that square root 4 is 2. We're going to keep that square root 2 because the idea with simplifying radicals is we are not going to pick up our calculator to try to get a decimal answer. Decimal answers for a lot of these radical numbers will be irrational numbers. Those decimals will go on forever and ever and ever and will never repeat. So we're going to leave them as square root 2 or square root 5 or cube root 3, whatever they may be. If we cannot simplify them, we are not going to use our calculator to try to get a numerical answer. And then we have this plus root 2 from the beginning. And now I have like radicals, square root 2 in both terms. We can take the coefficients, factoring out that square root 2, or using the distributive property in reverse. We can pull the square root 2 out, and we add the coefficients in the front to get 3 square root 2, which is our answer. I'll leave the square root 20 plus 5 root 5 for you to try. Let's take a look at 5 root 2 plus root 50 plus root 72. 5 root 2 is simplified. There's nothing we can do there, so we will copy it over. Square root 50 does have a perfect square factor of 25. 25 is the largest, so let's pull that out. And for 72, 9 times 8 is 72, but 9's not the largest. You could still go that route, just as we had in previous lessons. Remember, there are multiple ways to come at these problems and still get a correct answer. But I recognize 36 as a perfect square factor of 72. So 36 times 2 will be what I replace 72 with. Using the product rule for radicals, I can split the radical across the multiplication and then simplify the perfect squares. Square root of 25 is 5. Square root of 36 is 6. And comparing my radicals, they all have an index of 2. They all have a radicand. The thing underneath the radical is 2. I can add these together. And we get 16 square root 2. Looking at this one with cube roots in it, x cube root 81 plus 3x cube root 3 plus 5 cube root 3. I think that 81 has a perfect cube in it. But that perfect cube is not 8. So let's see if we can find out what perfect cube 81 is. I know 81 is 9 times 9. And I also know that 9 is 3 times 3. And check it out. I have 3 3s, which would be 27. 27 is my perfect third power factor of 81. And I found it just by trying to get it down to trying to get 81 down to its prime factorization. And we have 4 3s there. We're going to take 3 of them as our perfect cube factor. I'll leave the x out front. Cube root 27 times 3. And then 3x cube root 3 plus 5 cube root 3. And we can break apart this first cube root, distribute the radical across the multiplication, because we're using that product property, product rule. We'll copy the rest of them over. And then cube root of 27 is 3. I'm going to just switch the order that I write these in because we like the variable to be after the coefficient instead of before it. And so now we have 3x cubed root 3 plus 3x cubed root 3 plus 5 cubed root 3. Looking at them, they all have the same index and the same radicand. That's promising, but there's one tiny problem. Two of the terms have an x, and the last one does not. Just like with like terms, we have this x showing up. We are only allowed to combine the first two terms. Because the last term does not have an x, there's no way to put it in with the 3x plus 3x. I can sort of show you what I mean in terms of factoring. So if we pull out that cube root 3 at the end, use that distributive property in reverse, we have 3x from the first term, 3x from the second term, and 5 from the third term. Now you can really see the like terms that happen. We have 3x and 3x, which are like terms, so we get 6x, but that 5 just has to hang there. We can't do anything with it. So we have 6x cubed root 3 plus 5 cubed root 3 as our final answer. Looking at the square root of 49x to the 5th minus the square root of x to the 5th, we can break apart the square root. 49x to the 5th, copy over the second term. Square root of 49 is 7. And you may be tempted right now to do the subtraction. You could. You want to make sure that your final answer does not have any perfect square factors underneath the radical, because if we do, we need to take them out. So we could say 7 minus 1 square root x to the 5th to end up with 6 square root x to the 5th. But we cannot stop there because of the x to the 5th part underneath the radical. X to the 5th, we could write it as x to the 4th times x to the 1st. We could also see that x to the 5th is x squared times x times x. There are a lot of different ways that we can group these x's so that it makes it convenient for us. Now, with the x squared times x squared, this is really x squared squared. I have two of them. They're identical. I could put it like this. I say that in that if we do it like this, x squared squared times x, then we can break apart the radical. 6 square root x squared squared square root x. And in doing that, the square root and this outside square cancel. And we're left with 6x squared square root x as the final answer. Or we could break it apart as squares. 6 square root x squared square root x. And we get that cancellation twice. But always keeping in mind between the numbers and the radical symbols is multiplication. 6x times square root x. We still get 6x squared square root x. Same answer that we got before. Multiple ways to approach the problem and still get a correct answer. Now looking at this fraction with also radicals in it, I see that I have like radicals in square root 2's, but I do not have like denominators. So I need to multiply by a special form of 1 on both of these fractions in order to get them into like denominators. And so to determine the LCD, least common denominator, 5 and 3 are both prime. They have no common factors. Our LCD needs to be 15. So for the first fraction, we'll multiply by 3 over 3. And for the second fraction, we'll multiply by 5 over 5. So that we get 15 in both denominators. And we are multiplying, so 3 times 7 is 21. Keep that square root 2. 3 times 5 is 15. 3 times 5 is 15 in the second fraction, and 15. Do not cancel those 15s. I know it's tempting. Don't do it. You'll be reducing what you just did, and you don't want to do that. You want to keep the common denominators. 21 minus 15. 21 minus 15 should be 6 root 2 over 15. 6 and 15 have a common factor of 3, so we can cancel out the 3's. And we end up with 2 root 2 over 5 as the final answer. Just to show you an alternative for this problem, 7 root 2 over 5 minus 3 root 2 over 3. It could have been wise to cancel the 3's here, so that we have 7 root 2 over 5 minus root 2. Put that over 1, and then we only have to multiply the second fraction by 5 over 5 to get common denominators. And 7 minus 5 gives us 2, and we get that same answer.